Okay, so in this video we're gonna go over how we can write an epsilon-delta proof, and I'll be giving examples to different kinds of questions that you may encounter. So for the first one, we have to know that, back to the definition, for all epsilon greater than 0, there exists a delta that's greater than 0 such that if this condition of, well, delta exists, then we can find an epsilon. That's it. So firstly, given that an epsilon greater than 0, which is, well, the first thing here, we can choose a delta value equal to, well, we don't know what the delta value is. That's what we want to check. That's what we want to know. So suppose that our x minus a, the absolute value of x minus a, is between a range of 0 and delta. Then the fourth step is that we check if it's true or not. We check if it's smaller than epsilon. Okay, so for the first example we're gonna give is a linear example, like of a linear function. So how do we write it? Now, firstly, again, given an epsilon greater than 0, and secondly, we choose delta equals to, we don't know what yet. And now for the third step, we suppose our x minus 3 is between the range of 0 and delta. Then we check if it's true or not. So check. So our f of x, which is 2x plus 4 minus our L, which is 10, then this whole thing equal to our 2x minus 6, and if we pull the 2 out, we will get 2 times x minus 3. And oh, we see here x minus 3 is between 0 and delta, so this thing is smaller than 2 delta, right? And now we have to check it if it's smaller than epsilon, so we can just set 2 delta equal to epsilon. Okay, so which means that the chosen delta equals to epsilon over 2. Yeah, that's basically it. That's how you can write a epsilon delta proof of a linear function. And nextly, we have a question of a quadratic function. Okay, now same approach. Firstly, given an epsilon greater than 0, choose a delta equal to, we don't know what, so we leave it blank first. Thirdly, suppose our absolute value of x minus 5 is between 0 and delta. Then we check if it's true. So check our function f of x, which is x squared minus 3. So x squared minus 3x. And then our L equals to 10, so minus 10. Okay, and now we can separate them into, well, x minus 5 and x plus 2. So, okay, the condition that we have is the absolute value of x minus 5. So we keep it as x minus 5 times our absolute value of x plus 2. So this x plus 2, what is it? It's basically just k, right? So this whole thing will be smaller than k delta. So now what do we have to find? We have to find what k should we choose, right? What k should we choose? We can basically choose, well, we have to like give a bubble, like make a bubble here. So x minus 5, right? We want it to be close to 5. So we can choose the range, let's say 0.1, 0.01, 0.0001, whatever we want to choose. But for here we can just choose, well, smaller than 1, let's say, like 1 unit. So if we choose it as 1 unit, then which means that our x minus 5, well, it's basically whatever unit you choose. You can choose 0.1, you can choose 2, you can choose 0.001, but for convenience, let's just write 1. Okay, so our x minus 5 is between -1 and 1, and we want to find x plus 2. So we make it x plus 2 by adding 7 to everything. So if we add 7 to everything, we have 6, and I have x plus 2, and I have an 8 here. 8. I almost wrote a delta. Okay, 8 here. So we can just choose k equals to 8, right? So we choose k equals to 8, then we get equal to, let's say 8 delta, and we choose this as our epsilon, meaning that we chose delta equals to epsilon over 8, right? So for this part, whatever k we choose, which is, well, we chose the range, well, we chose that x minus 5 is between the range of -1 and 1. So therefore we get a corresponding k value that we can put, right? We can also put 7. Okay, now here we choose it as 1 doesn't mean that delta equals 1, right? Even if delta is 0.0001, this equation also satisfies the equation, the inequality, because what if let's say x minus 5, the absolute value, is 0.00001, it still satisfies that it's smaller than 1, right? It doesn't matter. So we can just set whatever we want over here, just not that big, just choose, let's say 1. Okay, so in this case we have our delta equals to epsilon over 8. Okay, now the next example, where it's a rational function, the limit of 1 over 2x plus 1 as x approaches 1 equals to 1/3. Okay, same approach. First, given our epsilon greater than 0, and then we choose delta equals to something. Now for third step, we suppose that the following is true. X minus 1 is between 0 and delta. Then we check. Okay, so our function, which is 1 over 2x plus 1, minus our L, which is 1 over 3. Well, how do we do this? How do we make it into something like x minus 1? Well, we don't know yet, so let's do whatever we can do, which is putting them together as one fraction. So we get 3 times 2x plus 1, which I can rewrite as 6x plus 3. Okay, and on the top we get 3 minus our 2x plus 1, which is 2 minus 2x, right? So we get 2 minus 2x. But since it's in an absolute value, so we can swap the negative. So it will be 2x minus 2. Okay, and from here, I can pull out the 2 and 3 here, and then it will be x minus 1, and below would be 2x plus 1. Okay, now we can set 2x plus 1 equals to k, or we don't have to, because either way it's gonna be smaller than 2/3 of x minus 1, right? Because this cannot be equal to 0. It cannot be equal to 0. It does not exist. So we can just leave it. Let's say it's 2. Okay, if it's 2, wait, no, never mind, sorry. if we plug 1 in, because x approaches to 1, right? If we plug 1 in here, it will be 3. So it will be either way smaller than our function of 2/3 the absolute value of x minus 1, which essentially is smaller than our 2/3 of our delta, right? Because our absolute value of x minus 1 is smaller than delta. So 2/3 of it will be smaller than 2/3 of delta. And here we can choose it as our epsilon. Okay, so 2/3 of delta equals to epsilon, meaning that our delta equals to 3/2 epsilon. So now we have it. We choose our delta equals to 3/2 epsilon. That's how you write a epsilon delta proof for a rational function. And the last example we have is our well, it's a how do you call that? Square root. Yeah, square root. Let me write it down. Square root. Well, just root. Okay. Again, given our epsilon greater than 0, we choose a delta equals to whatever. We don't know yet. Then we suppose that x minus 3 is between 0 and delta. And now we check if it's true or not. Check. So our function is the square root of 3x minus 5. And then our L is minus 2. Okay, now how do we make it to the absolute value of x minus 3? Well, we rationalize it first. So how we do that is we multiply everything by minus 2. So we multiply everything by the function, which is square root of 3x minus 5 plus 2. Okay, and then we divide by the same thing. Okay, and then for the numerator, we get 3x minus 5, well, the square root of 3x minus 5 squared, which is 3x minus 5, and then minus 4, because 2 squared is 4. Yep, and everything over our 3x minus 5 plus 2. So if we rearrange everything, we get our 3x minus 9 over square root of 3x minus 5 plus 2. If we take the 3 out, we get 3 over the absolute value of square root 3x minus 5 plus 2 times the absolute value of x minus 3, which is delta, well, which is smaller than delta here. So we can choose, well, this is basically just a random constant k, right? And either way, it's gonna be greater than 1. So we can just say that everything that we have is smaller than our 3 times x minus 3, the absolute value of x minus 3, which is smaller than 3 delta, because as we know, the absolute value of x minus 3 is smaller than delta. So 3 times of it will be smaller than 3 times of delta. And for this, we choose 3 delta as our epsilon. And now we get epsilon equals to, delta equals to epsilon over 3. Well, it looks like a mirror where it's upside down. Okay, so we choose delta equals to epsilon over 3. So that's basically it. That's how you can write a epsilon delta definition for, well, basically any question that you see. You write down these 4 steps. Given epsilon greater than 0, we choose delta equals to, and we leave it blank first. And we suppose that for this delta is true, then we check if it's true for the epsilon. And remember, for the checking part, we always have to make it so that it has the expression of the supposed thing, because we want to write delta in terms of epsilon. Okay, I hope you understand these examples and how to write an epsilon delta definition. And I'll see you guys in the next video where we'll be covering some computation techniques of our limits. See you then. Bye bye.